So in this video we will be discussing about errors of measurement. But before that, I want to let's discuss something about significant figure. Now significant figure in the measured value of a physical quantity tells the number of digits in which we have confidence. Larger the number of significant figures obtained in a measurement, greater is the accuracy of measurement. The reverse is also true. Now, conventionally, the number of digits which are known accurately plus the last one digit whose value is known only approximately, they forms the significant figure. For example, when we measure the length of a straight line using a meter rod, suppose it lies between 12.4 centimeter to 12.5 centimeter. Okay. Now we can estimate that L is around, suppose we have estimated at 12.48 centimeter. This expression has four significant figures. 1, 2, 3, 4. This expression has four significant figures. Now out of these, 1, 2 and 4 are precisely known, but this is only approximately known because it lies between 4 to 5 and we have approximated to be 12.48. Now, the significant figures now of a physical quantity that also depends upon the least count of the measuring instrument. So, lower the least count, more will be the number of significant figures and more is the accuracy. Now suppose we are measuring the thickness of anything like thickness of a wooden slide, glass slide, iron slide, whatever. Take it as a glass slide. Now suppose in a vernier caliper, the thickness reading comes out to be 0.13 centimeter. But same thing, if we can use an instrument called screw gauge, suppose, just suppose, the thickness comes out to be 0.136 centimeter. Now this value, this one, has three significant figures. This has two. So you can say this is more accurate than this one. There are certain rules also to find the significant figures. Rule 1 is all non-zero digits are significant. So this is the first one. Non-zero digits like 1, 8, 9, 7. This number has four significant figures. Rule number 2. All zeros occurring between two non-zero numbers are significant figure. 7, 0, 0, 0, 8. 1, 2, 3, 4, 5. 5 significant figures. 1.097. 1, 2, 3, 4. 4 significant figures. Rule number 3. If a number is less than 1, meaning in points, all zeros to the right of decimal point and to the left of a non-zero digits, they are not significant. Like 0.0095. This is rule number 3. This will have two significant figures. So this is not valid. But if you take 1.0095, this will have 1, 2, 3, 4, 5. 5 significant figures according to rule 2. Now, rule number 4. All zeros on the last of a non-zero digit in a decimal point parts are significant. Like if suppose 0.00900 has three significant figures. 1, 2, 3. 3 significant figures. So basically all zeros on the right of the last non-zero digit in a decimal part are significant. Rule number 5. All zeros on the right of a non-zero digits are not significant, like 37000. It has only two significant figures. But this rule number 6 states that if this represents a measurement like 37000 meter, then 1, 2, 3, 4, 5. Then they have 5 significant figures. Okay. Now some arithmetical operations like addition and subtraction. Addition and subtraction. addition and subtraction. Now addition and subtraction of numbers, like in addition and subtraction, the numbers of decimal places in the result should equal the smallest number of decimal places in terms of the operations. Now means the final result should be expressed as the least number of significant figures in all measurement. Suppose you take 2.1 meter, 1.78 meter, 2.046 meter. Okay, now if you add all of them, this will be 5.926 meter. But what is the smallest significant figure? 2.1. So your final answer should be in two significant figures only. The final answer is 5.9 meters. On multiplication and division, in multiplication and division, the number of significant figure in the product or the quotient is same as the smallest number of significant figures in any of the factors. Same as of addition and subtraction, means the final answer should be given in the significant figures, which is equals to the least number in any one of the given number. Now suppose we are multiplying two numbers like 4.6 into 0.128. So if you multiply them, you see that the answer is what? It comes out to be around 0.58. Then you can do it in a calculator also, or just try to multiply. But our answer should be up to 2 decimal places, 4.6. So we round it off. Answer is 0.59. Okay, now suppose division, just take the number 0.9995 times 1.53. This is 1.592. So basically this comes out to be 0.96057 and so on. But what is the least? Least is 3 significant figures. So this will be, round it off, this will be 0.961. So this is the number which we have expressed the answer as the least significant digits. Okay. Now our topic was errors of measurement. We know that measuring process is essentially a process of comparison. Now to measure any physical quantity, we compare it with the standard unit of that quantity. Suppose taking the same example of like measuring the length of the table. So we have chosen the unit meter. So then we compare it with the meter. Like suppose the length of the table is 4 meter. So basically that is, table is 4 times the unit of length. That was the comparison mean. No measurement is perfect as the error involved in the process cannot be removed completely. And in spite of our best effort, the measured value of quantity is somewhat different from its actual value, or you can say the true value. So now there are two terms, measured value and the actual value. The difference in the true value and the measured value of a quantity is called the error of measurement. The difference between the true value and the measured value. Now in this our topic, we will be discussing absolute error, relative error and the percentage error. Okay. Absolute error, relative error, and percentage error. Percentage error. Now, starting with the absolute error. Sorry, I have written the S. Okay. Absolute error. So, absolute error is a measurement of a physical quantity. In a physical quantity is the magnitude. Again, the difference between the true value and the measured value of a quantity. Now, suppose we are measuring a physical quantity and we have measured n times. So let the measured values be A1, A2, A3 and so on up to AN. These are the measured values. Okay. Now we have to find the arithmetic mean. We usually find the arithmetic mean. So the arithmetic mean is given as A1 plus A2 plus A3 plus and so on up to n divided by n. So this is the measured value. Now, measured value. So usually AM is taken as actually these are the measured value. This is taken as the true value of the quantity because we are taking the mean of all this. So, okay. Now, by the definition of absolute error, in the measured quantities, in the measured values of quantity are, now see, delta A1, this is the absolute error. So we find it by AM minus A1. Delta A2 will be AM minus A2. Delta A3 will be AM minus A3. And so on you goes like this till you get delta AN equals AM minus AN. So this is what the absolute error is. The absolute error, this point is to be noted. The absolute error can be positive and in some cases it can be negative. Now, the mean absolute error. Mean absolute error. So basically mean absolute error is the arithmetic mean of magnitudes of these absolute errors in all the measurement of a quantity. Basically this is represented as delta A and then bar, the mean absolute error. So thus delta A bar is equals to, now see I am using the modulus sign. So you know what's modulus. Even if that quantity is negative, we will use the positive sign only, this modulus upon n. So this is the mean absolute error. And the final result of measurement can be written as A equals AM. This is plus minus delta A bar. So this implies that measurement is basically to be lies between AM plus delta A bar and AM minus delta A bar. So this delta A bar is what? The mean absolute error. Just find the mean of all these absolute error. Delta A bar. Now, the relative error or the fractional error. Fractional error. The relative or the fractional error of a measurement is defined as the ratio of mean absolute error to the mean value of the quantity. So this is basically delta A bar, the mean absolute error upon the AM. This is the mean value. So if you do delta A bar upon AM, that gives you the mean value. Now percentage error will be, percentage error is just delta A this by AM, you do times 100. You get the percentage error. So now this theory can be illustrated by taking an example. Okay. Now the refractive index is water is found to have the values. So you know the refractive index as we have done in 10th class. This is 1.29, 1.33, 1.34, 1.35, 1.32, 1.36, 1.30, 1.33. Now you have to calculate the mean value, the absolute error, the relative error and the percentage error. So first of all we know the mean of all refractive index will be. So let it be refractive index, as we can represent it by anything, is represented by the letter which is called mu. So mean error will be, you add all of them divided by 1, 2, 3, 4, 5, 6, 7, 8. So there are 8 values. So you add all of them, 1.29 plus 1.33 plus 1.34 plus 1.35 plus 1.32 plus 1.36 plus 1.30 plus 1.33. You can then add it, divide it by 0. And the answer is basically 1.3275 on solving it. But that has to be rounded again up to 2 decimal places, 1.29, or up to 3 significant figure, which is the least one. So mu is 1.33. So this is the mean value. Okay. Now, absolute error in the measurement will be given by, now see, absolute error. Now this is mu 1.33. So 1.33 minus 1.29. 1.33 minus 1.33, and so on. So just to illustrate this, just like this as absolute error, in measurement. So absolute error in measurements are, let it be represented by delta mu 1, which is 1.33 minus 1.29, which is 0.04. So 1.33 minus 1.29. So next will be again 1.33 minus this, 1.33 minus 1.34, 1.33, 1.35, 1.33, 1.32, and so on. We will do that. Okay. So delta mu 1 is here. So there are delta mu 8. So delta mu 2. Let me write. So as I told you that absolute error in measurements are represented by delta mu 1, delta mu 2, delta mu 3, and so on. 1.33 minus 1.29, 1.33 minus 1.33, 1.33 minus 1.34. So here are the results. Delta mu 1, mu 2, mu 3, mu 4, mu 5, mu 6, mu 7, mu 8. And this is 0.04, and as you can see, minus 0.01, minus 0.02, plus 0.01, minus 0.03, plus 0.03, and this is 0, 0. Okay. Now we have to find the mean absolute error. So mean absolute error will be, you add all of this with the modulus value, we will take only the positive value, divided by 8. 1, 2, 3, 4, 5, 6, 7, 8. So if you do that, this will be, now this will be 0.04 plus 0.00 plus 0.01. Why? Because we have to take only the positive value, plus 0.02 plus 0.01 plus 0.03 plus 0.03 plus 0.00 divided by 8, which comes out to be 0.02. Now 0.02, this is the mean absolute error. Okay. Now what will be the relative error? Relative error or the fractional error. So we write relative error is equals this thing, 0.02 upon the measured value. Measured value is 1.33. This is 1.33. Okay, we can write this. This is actually delta mu, which is bar, upon mu. You can write m or just mu there. So this is actually plus minus 0.02 upon 1.33. Percentage error. Percentage error, you know that this is actually equals to, this is actually equals to plus minus 0.015, expressing this as 2 decimal place, so this is 0.02 plus minus. Okay, so percentage error, taking this value 0.015 into 100, so which is plus minus 1.5%. So now propagation or the combination of errors. Propagation or combination of errors. Now we know that as a result of experiment is calculated by performing mathematical operations like addition, subtraction, multiplication, division and raising to some power, etc. on several measurement which will have different degrees of accuracy. To calculate the net error in the result, we should study how errors propagate in different mathematical operations. Now what we are going to do in this video is that we will discuss each propagation of error in the 5 different mathematical operations like addition, then subtraction, then multiplication, division, and when raising to some power, etc. So error in summation is basically the addition one. Now suppose we get a quantity x which is actually the result of a plus b. A plus b. Okay, means we are getting a by adding a plus b. Now what is delta a? Now delta a, let it be the absolute error, ABS, absolute error in the measurement of a, in measurement of a. Delta b, same thing, absolute error in the measurement of b, and let it be delta x, be the absolute error in the, not measurement, like absolute error in calculation, okay, in calculation of x. Now the result will be that you should memorize this thing, that delta x is equals to plus minus of delta a plus delta b. Now this point is to be noted. So the maximum absolute error in the sum of two quantities is equal to the sum of the absolute errors of the individual quantities. So basically to get delta x, we have to add these delta a and delta b. Okay. Now the second is what? The errors in difference. Second is the errors in difference. So let x is equals to a minus b. Okay. Delta a is what? The absolute error in the measurement of a. Delta b is the absolute error in the measurement of b, and delta x is the absolute error in the calculation of x. Again, in case of difference, you will see we will have the same result. Delta x is equals to plus minus delta a plus delta b. So again, the maximum absolute error of two different quantities is equals to the sum of the absolute errors in the individual quantities. So we can understand this error in summation and error in difference by an example. Now in experiment, two capacities measured are. Now these are the two capacities measured are 1.3 plus minus 0.1. Now this is mu f. Mu f is actually microfarad. This is the unit of capacity which we will learn further videos. And 2.4 plus minus 0.2 microfarad. Now calculate the total capacity. Total capacity means in parallel. So in parallel we actually add them with percentage error. Okay. Now, so what is given to us? Let this be C1 is 1.3 plus minus 0.1 microfarad, and is given to you is C2, which is 2.4 plus minus 0.2 microfarad. Okay. So in parallel connection, basically we add them. In parallel, let it be Cp with the result which is equals to C1 plus C2. So yeah. So in parallel circuit, Cp is equals to C1 plus C2. We combine that. Now, what will be Cp? C1 plus C2. that is 1.3 plus 2.4. So this will be 3.7 microfarad. Okay, now we have to find delta Cp. As we know in summation, delta Cp will be plus minus delta C1 plus delta C2. Now just add them, plus minus, this is 0.1 plus this is 0.2, which is equals to plus minus 0.3. Okay, so this is delta Cp. Now the percentage error. To get the percentage error, this is 0.3 upon 3.7. We can write plus minus into 100, which comes out to be plus minus 8.1%. Hence, the final value of Cp can be written like 3.7 microfarad plus minus 8.1%. Okay. Example is the initial and final temperature of water as recorded by the observer are 40.6 plus minus 0.2 and 78.3 plus minus 0.3 degrees Celsius. Calculate the rise in temperature with proper error limits. Now see, you can write temperature as theta. So theta 1, this is theta 1, which is equals to 40.6 plus minus 0.2 degrees Celsius, and theta 2 as 78.3 plus minus 0.3 degrees Celsius. Okay, now they are saying rise in temperature. The rise in temperature is basically the difference. So rise in temperature is given as theta equals to theta 1 minus, or you can have theta 2 minus theta 1. Now see, this is of higher temperature. So we are finding the rise in temperature, so with highest minus lower, you can say final minus initial, to which is 78.3 minus 40.6, which is equal to 37.7 degrees Celsius. Now this is the rise in temperature. Okay, so or you can write this as delta theta actually. So delta theta is 37.7 degrees Celsius. Now okay, no, don't write delta theta, because since this is not the difference, this will be theta only, because delta theta we will represent the like absolute error, the errors like delta theta. Now what will be delta theta? This will be actually equals to plus minus theta delta theta 1 plus delta theta 2. I'm sorry for this, because sometimes we use delta, we represent delta for the change. That's why I was a bit confused. Okay, so this is, again, though it's minus, but still, as we have learned in difference also, we add the errors. So this is plus minus 0.2 plus 0.3, which is equals to plus minus 0.5 degree Celsius. So rise in temperature will be 37.7 plus minus 0.5 degrees Celsius. Degrees Celsius.